on?
So in class we talked about diffraction gratings when we talked about X-ray diffraction and X-ray scattering. So I'm going to talk a little bit about diffraction gratings, and then I'll show one of the applications of diffraction gratings. So diffraction gratings are a grating with slits a distance d apart. And we can think about them with this equation here, where this lambda is the wavelength of the incoming light, d is that distance, and m is the order of the maxima in the diffraction pattern. And then this theta is going to be the angle made with the central axis. So this is a pretty interesting principle that we can describe with a fairly basic equation. And we're actually going to translate this diffraction grating to something that's programmable. So we will actually program diffraction gratings here with a liquid crystal display. So the way liquid crystal displays work is they're made up of liquid crystal molecules, and these liquid crystal molecules rotate as you pass a voltage over them. So they're kind of football shaped, and if I were to pass a voltage through the liquid crystal molecule, it would rotate. So we can kind of think about this area that a liquid crystal molecule would cover, and as I pass a voltage through it, it'll rotate. And you see as it rotates, it lets in more light, or it can let in less light. And we'll use that principle to program our diffraction gratings. So there's a few types of diffraction gratings. This is a more typical one we might see, like the one over there, where this distance d between the slits of the diffraction grating is a linear quantity. And that's very nice, but that's not what we typically use. We'll use a diffraction pattern that looks more like this. So this diffraction pattern has a distance d that's actually going to vary as a function of radius. So it's going to vary as we move across the screen away from this origin. And you can see we have these nice rings here that represent that. And something weird will happen when we use this in an optical system. It's actually going to act like a lens. It's a diffractive lens. So we can just describe it with our lens equation. That probably saw this in Physics 197, but we can use this very simple equation to describe a lens, and even it works with diffractive lenses. So we'll have some lens. This f is going to be the focal length of that lens, and then these are going to be some distances with this system. So this distance p is going to be the distance between the lens and an object that's being imaged with this lens. So light rays are going to come in like that, and then they're going to come to a focus over here. And then this distance is going to be q, the distance between the lens and the focused image. So if we come around here, we have a diffraction pattern that we've programmed. You can see it's going to vary radially as we come out from the center. And this is something that we can program to have a certain focal length. And we'll do that here. So this is our helium neon laser. We're going to pass that through a lens first, actually. And this lens is just collimating the beam, and all that means is that it's pointing all the rays of light so that they're parallel to each other. So that distance p that we talked about between the object and the lens that's imaging it, we don't have to worry about that, because it's basically infinity since all the rays are parallel to each other. So all we have to worry about is this distance here and the focal length. So I've programmed a 70 centimeter focal length lens on this, which means since that distance is infinity, this is going to be a 70 centimeter distance. And we see that here on the pattern. You can see it's focused, and if I move it towards our lens, it'll come out of focus. It'll be back in focus here at 70 centimeters, and it's out of focus again, away from the 70 centimeters. So this is one of many applications of diffraction gratings. They're very interesting. You can program them to do all types of things.